All right, welcome to our final lesson in Unit 4 that we're going to be concerned with, which is 4.4 orthonormal basis in Graham-Schmidt process, which ends up leading into an algorithm and things like that later on. Really what I want to do in this kind of a part 1 video is keep it very short, keep the second one short as well, and then essentially give the example for when we're solving the Graham-Schmidt and walking through that algorithm. Really just in this part, focusing on our driving questions, which is why do we want to construct orthogonal basis? So why do we want orthogonal vectors? And then how do we actually create an orthonormal basis, and why specifically, and what specifically does orthonormal imply? Really, he highlights this, he gives some examples of the bases themselves, the purpose of them, and I'll highlight some of that. But really the purpose is why orthogonal is, remember that orthogonal vectors, their dot products are 0, and if you dot product it with itself, you would get its unit length. And so orthogonal vectors that are 90 degrees to one another make calculations much easier to deal with. So for example, if I had a matrix that had orthogonal columns, then ATA is equal to a diagonal matrix. Diagonal matrix implies that there's only non-zero entries along the main diagonal, and then every other entry is 0. So it makes our calculations much simpler when we're working through our 3 equations that we saw from doing our projection section. And I'm going to highlight that a little bit more in a minute. And so this is really the biggest reason why we care about taking a matrix A and finding an orthonormal and orthogonal basis for it, because then once we find that basis for that matrix, we can use those vectors for the calculations instead. And again, the math behind it and then the computations needed to solve becomes much, much simpler, and we'll see that throughout these units here. So that's the main reason. And so another reason we'll kind of see in a second, once we have kind of really defined what orthonormal means. Orthonormal is orthogonality, so the vectors are 90 degrees, they're perpendicular to each other, so their dot products would be 0. But not only that, they have unit lengths, so each column only has a magnitude of 1. And that's what it means by orthonormal. Orthonormal implies orthogonal columns where each column has a length of 1. And so if I have this, then the diagonal matrix that gets created by doing ATA becomes very, very unique. If I call an orthogonal matrix Q, more specifically orthonormal Q, then if I do Q transpose times Q, I'm going to get a diagonal matrix, but that diagonal matrix is the identity matrix. And the definition for this essentially stems from when I do Qi transpose Qj, this is going to come out to be 0 when I is not equal to j, and it is 1 when I is equal to j. Because when I take the dot product of the same column vector, that should be equal to 1 if that vector has a length of 1. And that's essentially where that dot product format comes from. And so now the calculations get even cleaner. One of the ways that I want to kind of show how that gets cleaner is then imagine again that we're, from our projections section, that if my matrix A, the matrix subspace that we want to project onto, that we created there, if those columns are linearly independent, which they will be if I have an orthonormal basis for it, we simplify our calculations so that over here, ATA, which is QTQ, comes out to be the identity matrix here. In other words, X hat, we get to be QTQ inverse QTB. Well, this is just the identity matrix, and the inverse of the identity matrix is the identity matrix. This is essentially just 1. It's I. We now have X hat is equal to just this. We don't have to compute an inverse. When we look through our projection matrix here, again, same thing happens. The projection matrix itself, to project any vector onto our subspace, is now QQT. So when I'm taking an orthonormal basis for my original columns, if I can transform them and find an orthonormal basis for them, all of our calculations and all of our equations get simpler. That's the why. The how we get to that is what we're going to get into with the Graham-Schmidt process and how we can construct that. The last thing I want to highlight here with orthonormal basis and orthonormal matrices in particular is that generally these matrices are m by n. In other words, they're rectangular, they're short and wide, essentially. And remember that if I have these short and wide matrices, the inverses then will not exist. But if I can use an orthonormal, then it doesn't matter, because even if I do QTQ, I'm still constructing an n by n matrix. We're constructing a square matrix that's I because it's orthonormal. So we get to avoid all of the pitfalls of a matrix that is m greater than n. Now, if my Q is a square matrix, so if I can form an orthonormal that's a square matrix, then what's actually really interesting is not only is Q transpose Q equal to I, but Q transpose is also equal to I. In other words, that the matrix is not only just a left-sided inverse, the transpose, but it's also a right-sided inverse. It's invertible from both sides. And so in this situation, it's not, because it's rectangular, but it's still left side invertible. It's just not right side invertible. This would create another matrix, specifically a diagonal matrix. We'll kind of see that play out a little bit later. But it's one of the other benefits here that if I have a rectangular matrix, we get to avoid the pitfalls of the inverse. And remember, we kind of were stuck with that in an earlier section because we couldn't really compute that very easily, so we had to solve the system A transpose A x hat is equal to A transpose B. We had to set up a whole new system and a whole new coefficient matrix and then augmented matrix to find x hat. And now we wouldn't have to do that. I can just solve this and do this multiplication. So the goal is to try and find that orthonormal basis. Now, he gives a couple of examples. These are really important examples for orthonormal basis, and they are essentially the transformations. So if you think back to algebra classes, if you think back to pre-cal, some much earlier math courses, whenever you want to transform functions, we have three main ways to transform functions and transform figures in general. One is we have rotations, we have reflections, and then we have permutations. There's really are three different ways that we can manipulate, at least in terms of matrices. Now in transformations for functions, we have translations, where we can move things left and right. But for us in particular, we can move columns. So I was kind of thinking translations as permutations. And so we got permutations, rotations, and reflections. And those matrices are given in the text on page 177 and 178, so I'm not going to highlight too much there. But the takeaway is that every permutation matrix is an orthogonal and orthonormal matrix. Every rotation is an orthonormal matrix. And every reflection is an orthonormal matrix. So each one of those fits in with these concepts here, which are really important. Again, just kind of highlighting that if Q has orthonormal columns, Q2Q is equal to I, it leaves the links unchanged because this won't affect the magnitude of whatever we're multiplying with. We're always multiplying essentially by a scalar of 1, so it's keeping all of our links and numbers used smaller. It's not scaling things, which is really, really important. And so hopefully this kind of helps clarify a little bit of the why, again, that he talks about in the book. Really kind of helps simplifying these examples. We will come into this and talk about the projections and the simplification a little bit more in the part 2 video, and we'll go ahead and jump into the example that's given there before jumping into the Graham-Schmidt process in part 3.